Welcome to this video. In this video, we're going to explore one of the most important topics in machine learning, loss functions and evaluation metrics. We'll look at different types of losses and metrics and discuss what factors you should consider when choosing them and when each one is appropriate. We'll revisit ROC and precision recall curves and see why looking at ROC alone is not enough to judge a model. We'll also explore how precision can be highly sensitive to the data and how even small changes in the dataset can lead to very different conclusions. Then we'll go through different types of loss functions, including advanced ones like focal loss, and understand when and why to use them. We'll also talk about offline and online metrics and why relying on a single metric is often not enough. Instead, we'll introduce the idea of a hierarchical approach to metrics to better align model evaluation with real-world goals. And finally, we'll see how to design a process that guides your model toward what actually matters for the business. Because in the end, we must look beyond just the numbers on a screen. It's not just about building a model. It's about building a system that creates real value.
Your model does not see the problem directly. It sees the problem through the loss function. And that matters a lot, because the loss function acts like a lens. It tells the model what to focus on, what to ignore, and what should count as a mistake. So even if you keep the same data, the same features, and the same model architecture, changing the loss function can lead to completely different behavior. If that lens is chosen correctly, the model moves in the right direction. But if that lens is wrong, the model may optimize the wrong thing and fail, even while the training process looks perfectly fine. That's why loss functions are not just mathematical formulas. They are one of the most important design choices in machine learning. In other words, your model understands the world through the loss function. To really understand this, let's look at a simple but powerful example. Imagine you have this data set. 9 values are 100, and 1 value is 1000. Now here's the interesting part. Depending on the loss function you use, your model will learn completely different things. Imagine we consider our MSE as our loss function. So the model says, the best single prediction for all data points is around 190. Why? Because MSE tries to match the mean of the data. If you compute the average, it is equal to 190. Now if we consider MAE as loss function, our predicted values become 100. Why? Because MAE tries to match the median of the data. Now look at the residuals of the two models. The model trained with RMSE, we have 9 negative 90, and 1 810. The sum of them equals 0. MSE balances errors so that the average error is close to 0. For the model trained with MAE, 90 and 190, the median is 0. MAE balances errors so that the median error is close to 0. Now let's calculate MSE and MAE as metric. For the model trained with RMSE, the MSE becomes 72,900 and MAE becomes 162. While for the model trained with MAE, the MSE becomes 81,000 and MAE becomes 90. No wonder the model optimized for MSE yields better MSE, as MSE tries to minimize the mean, so the mean residuals are better. On the other hand, the model optimized for MAE delivers better MAE, and as MAE tries to optimize the median residuals are better. But what does it mean for us? Which loss function is better? That depends on our application. Let's say we are optimizing a navigation system for aircraft, and an error larger than 850 means that a plane will go off a landing field and crash. In this case, optimizing for MAE is not an ideal decision. Of course, we can say 9 out of 10 times that we have a perfect result, and only 1 out of 10 times a vehicle is destroyed. But this is not acceptable by any means. We have to avoid outliers at all costs and penalize them. Thus, using MSE is a wiser decision. Now consider this example. Imagine you're running a cryptocurrency exchange, and every day you need to decide how much liquidity to keep. Now here's the interesting part. Suppose your data looks like this. 9 days you need 100 units, and 1 day you need 1,000. If you train your model with MSE, it predicts around 190. That means most days, you're over-allocating. And on the worst day, you're still under-allocating by a lot. But if you train with MAE, the model predicts 100. Now you're exactly right. 9 times out of 10. And only wrong in that extreme case. Why? Because as discussed earlier, MAE balances errors so that the median error is close to zero. So which one is better? That depends on your business. If underallocating is not drastically worse than overallocating, then MAE is actually the better choice. And this is the key idea. The best model is not the one with the lowest error. It's the one that makes the best decisions for your problem. Now let's turn our attention to loss functions used in classification problems. If the task is binary classification, we typically use binary cross-entropy. For multi-class classification, if the labels are one-hot encoded, we use categorical cross-entropy. And if the labels are represented as integers, we use sparse categorical cross-entropy. Focal loss is a modified version of cross-entropy designed for imbalanced data sets. Let's briefly understand what focal loss is and how it extends cross-entropy. In a standard classification problem, we use cross-entropy loss, which is defined as, here, Pi is the predicted probability for the correct class of sample I, and we sum over all training samples. During training, we try to minimize this loss using gradient descent. Each sample contributes to the total loss and, more importantly, to the gradient, which updates the model. So naturally, a key question is, do all samples contribute equally to learning? In standard cross-entropy, the answer is mostly yes. Even if a sample is already easy and correctly classified, it still contributes to both the loss and the gradients. But in focal loss, we introduce a coefficient to the standard cross-entropy loss to control the contribution of each sample. If Pi is high, meaning the sample is easy and correctly classified, the weight shrinks and its contribution becomes negligible. On the other hand, if Pi is low, meaning the sample is hard, the weight remains large, and the model focuses more on that sample. The parameter gamma controls how strongly this effect is applied, determining how quickly easy examples are down-weighted. We've seen that when dealing with class imbalance, it's important to choose a loss function that can handle it effectively. The same idea applies to evaluation metrics as well. Some metrics, such as precision, are highly sensitive to class imbalance, while others, like recall and specificity, are less affected. Imagine that we have a model that has a probability of 95% to predict that fraud is fraud, and 5% to predict that non-fraud is fraud. Let's review 3 scenarios where P is the number of positive samples and N is the number of negative samples. Keep in mind that this is simply a shorthand way of saying that the true positive rate TPR is 95%, and the false positive rate FPR is 5%. If you calculate precision, you'll see that when the two classes are balanced, it is around 0.95. When the positive class is abundant, it increases to about 0.99947. But when the positive class is rare, it drops significantly to around 0.65. You can see that severe changes in class distribution lead to dramatic variations in model precision, even when model parameters TPR and FPR are fixed. Let's look at 2 different ways to evaluate the same model. Here we have the ROC curve, and as you can see, the AUC is around 0.98, which looks amazing. If you only look at this, you would say, this is a great model. But is that really a correct evaluation? Let's look at the precision recall curve. As we can see, when we want to catch more positive cases, precision drops significantly. That means, the more fraud cases we detect, the more false positives we generate. So the model is not as good as it first appeared. This is exactly why choosing the right metric matters. If this doesn't fully make sense yet, I've got you. Just watch the videos on your screen where I explain this in more detail. ROC curve focuses on how well the model separates classes overall. But precision recall tells us what really happens when we care about the positive class. So depending on what you measure, the same model can look either excellent or problematic.
So far, we've learned something very important. A good metric is highly dependent on your business goals. Depending on what you care about, a model can look excellent under one metric and completely misleading under another. So relying on a single metric is often not enough. Instead, we need to think in terms of a chain of metrics, a set of measurements that guide us from model performance all the way to real-world impact. And this is where concepts like offline metrics, online metrics, and hierarchical evaluation come into play. A model is only as good as the metric you choose to evaluate it. In the rest of this video, I'm going to walk you through these ideas and show you how to use them in practice.
Before we deploy a model, we usually evaluate it using metrics like accuracy, F1 score, MSE and AUC. These are what we call offline metrics. They are calculated on validation or test data, and they help us quickly understand if the model is improving. But here's the catch. These metrics are just proxies. They are not the real goal. They are only an approximation of what we actually care about. You might improve your AUC, but in the real world, your revenue or conversion rate might not improve at all. So a better offline metric does not always mean a better system. Once the model is deployed, we move to online metrics. These are measured in the real world, with real users. For example, click-through rate, conversion rate, user engagement, latency, number of complaints. These metrics are much closer to reality. They tell us how the model performs in production. And then we have the most important thing, the final goal. This is what the business actually cares about. For example, increasing revenue, reducing churn, improving customer satisfaction, minimizing out of stock. Sometimes the final metric that truly matters for the business is very difficult and slow to measure. So we need to find a proxy metric that can be measured earlier and more easily, and that has a strong correlation with the ultimate goal. Suppose you're building a recommender system for an e-commerce website. The ultimate business goal is to increase GMV, gross merchandise value, total sales value. But what's the problem? You can't as easily or quickly measure GMV during the training or validation phase. You usually need to deploy the system, run an A/B test, and then see if sales have actually increased. And this is exactly the concept of hierarchy of metrics, meaning, if CTR increases, clicks increase. If clicks increase, CR conversion rate becomes more meaningful or tends to improve. If conversion increases, the number of purchases increases. If the number of purchases increases, GMV goes up. So CTR can serve as a proxy metric for downstream outcomes. Let's see what are the benefits of choosing CTR as a proxy metric. Imagine that in the recommender system we build for our online shop. We want to measure the effectiveness of the system based on its impact on total sales. Imagine on average, about 3% of our recommendations are clicked, and only 3% of those clicks lead to a purchase. So if we show 10,000 offers, first, we get about 300 clicks. Then from those clicks, only around 9 turn into purchases. So in the end, that's just 9 purchases. Because the positive class becomes extremely small. If the ultimate goal is purchases out of 10,000 impression, you only have 9 positives. That means, positive class or purchase equals 9. Negative class or no purchase equals 9,991. This is severe class imbalance. And this rarity, it causes 2 gigantic problems. First off, your model has almost no success examples to learn from. It's the classic needle in a haystack problem. And second, running an A/B test to see if your new model is actually any better would take forever. I mean, you need millions and millions of views just to see if you could nudge those 9 purchases up to 10. It's just not practical. But if we use CTR as a proxy metric because clicks happen much more frequently than purchases, purchase rate equals 0.0009, click rate equals 0.03. That means clicks occur approximately 33.3 times more often than purchases. Therefore, there are many more positive samples. Training is faster. Offline estimation improves, and AAB tests reach conclusions more quickly.
The antidote to all this potential chaos, it's simple really, process. You have to formalize this entire structure before you even write a single line of code, creating a design document for your metrics hierarchy. A well-defined metrics hierarchy isn't just an exercise, it's the essential bridge connecting your model's code to the bottom line. It's how you make sure that when your model gets better, the company's revenue goes up too. It connects the dots. Every single metric you track is telling a story. It's shaping your product and guiding every decision you make. So the question you have to ask yourself is this: are you really sure you're listening to the right one? Thank you for watching. Please support me by subscribing and sharing this video. Stay tuned for more.